it's a great pleasure and honor to have Vasily Belokurov from Institute of Astronomy, Cambridge, here as our guest speaker. He is an expert on galactic structure, substructure, tidal streams, gravitational lensing, microlensing, surveys like Gaia, SDSS, Oval, Ray, SST, etc. And machine learning techniques. He started his PhD in Oxford in theoretical physics, and finished his PhD in 2003. Then he moved to Cambridge, where he started a postdoc and then went gradually on the ladder and is now a reader at the Institute of Astronomy. And so today, he's going to talk about dark matter with tether streams. So let's welcome him to Heidelberg and look forward to it.
Thank you. Thank you very much for your kind words and for the invitation. I'll just go into it straight away because I know we run out of time by now also. So, what do we want to know about dark matter? We pretty much want to know most things because it's at the moment very mysterious and poorly studied substance. We hope that in the galaxy, in the Milky Way, we can do it best. We hope that the Milky Way is the best equipped laboratory to study dark matter properties. What do we want to learn about Milky Way's dark matter halo? It sounds ridiculous, but at the moment we don't really know the total mass of dark matter in the Milky Way with any good accuracy. So this is the first thing to constrain. We actually want to do a bit more. We want to also measure the radial profile in density distribution of dark matter. We also want to figure out what the shape of the dark matter halo is and how it changes with radius. An interesting question that is connected to the nature of dark matter particle itself is how far down in mass the subhalo mass function extends. So we want observational constraints on the dark matter subhalo mass function. So all these things I propose we can do in the Milky Way with stellar streams. Just to give you a little bit more motivation, why do we care about mass, for example? So Gaia is out there measuring positions and brightnesses and motions of billion stars in the galaxy. So we'll have this puzzle of the Milky Way assembled for us eventually with the Gaia data. But to be able to compare it to the models that we have of structure formation, we need to know in what dark matter halo the galaxy lives. So that's one primary motivation in figuring out the total mass of the galaxy. And of course, the traditional way of measuring the mass in the Milky Way is through spherical Jeans modeling. You can make it less spherical if you want, but it's Jeans modeling nonetheless, and there are problems with it. There is a well-known anisotropy where you have to know very well the density of your tracers and, the degeneracy, where you have to know the density of your tracers and the anisotropy of their orbits if you want to measure the mass. It turns out, to begin with, there are not so many tracers to measure the mass. So I'm going to use this interesting point, I like it still. So this is the galactocentric distance, and this is the velocity of the tracer, line of sight velocity. And you can see that past 40 or so kiloparsecs, the density of tracers drops dramatically. And that's all we have available to constrain the mass. And of course, the virial radius is off the plot. So that's why Jeans modeling is tough in the galaxy. But moreover, we don't actually know, because we have so few tracers, we don't actually know what the density distribution is. And of course, we have no idea what the anisotropy of the orbits is. So we have to guess that. So we need a better tool than Jeans modeling to constrain the total mass of the Milky Way. We want to know the dark matter halo's concentration and shape. And of course, the shape also reflects the nature of dark matter particles. So in Lambda CDM, we know that most of the halos we have created in a computer look quite correlate. Of course, the shape and the radial profile also encodes the accretion history, which we're also keen to know what the mass accretion history was on the Milky Way galaxy. The complication here is that the dark matter distribution, the radial profile and its shape must have been changed, reshaped by the baryon feedback. And of course, baryons can drag dark matter with it and make it more concentrated or more puffed up. So we want to understand how this coupling happens. And of course, to begin with, the shape was not constant with radius, but by influence of baryons onto dark matter, it's now definitely not constant with radius. So it's changing from the galactic center to the outskirts. So we want to measure that too. And knowing the dark matter density as a function of radius is important if we want to, have any hope to have successful direct detection experiments or indirect dark matter annihilation probes. If we want to understand why the galaxy formed a bulge or didn't form any prominent bulge at all. We know that if we take the cosmic microwave background and we use the initial conditions that we have frozen for us in the early universe and run forward our structure formation simulations to redshift 0, that's what we end up with for the Milky Way. It's pretty dark matter, but it's also highly substructured. You see that the small subhalos that formed the earliest in the universe managed to survive to today's epoch, and they're still intact, bound, orbits in the Milky Way halo. So there is this huge structure, this cloud of dark matter. Within, it contains swarms of smaller dark matter subhalos, and we have an idea of what the mass function, which is shown on the right panel, of these subhalos should be, but we actually want an observational constraint on that. Some of these subhalos will have accreted and cooled enough gas to form stars from it, and so they will host a dwarf galaxy inside them. But probably not all. For example, we think that potential host sites for dwarf galaxies in the Milky Way, these are the subhalos that today have virial masses in excess of 10 to the 7 solar masses. So of these, we have a order of 1,000 and 1,500. We think, by looking at the dwarf galaxy sensors around us, that we have at least 100 dwarf galaxies, maybe slightly more, which means that more than a half, or potentially much more than a half, of these 1,500 subhalos with masses in excess of 10 to the 7 will be completely dark. If that's true, we want to find them. So if we could look at our own galaxy from afar, that's how it would look like. And this is, of course, our nearest neighbor, Andromeda. What we've learned recently is that it is surrounded by this mass of the stellar halo. And it's messy because what it is made of is the debris, stellar debris, from dwarf galaxies that fell into the gravitational potential of Andromeda, disrupted, and their stars are now part of the stellar halo that is highly substructured. These are density of stars, and they're color-coded by their metallicity. So each star had to be detected, its colors had to be measured, and the colors were turned into metallicity estimate, and then this map is built. So we believe that something like this exists around the Milky Way. We want to use these streams and these shells, these substructures, to measure the properties of the dark matter. So the stars in the streams, they are tracers of the gravitational potential, and the gravitational potential, the mass budget, is dominated by the dark matter, to which the stars contribute almost nothing. We have a very good idea how to make a stellar halo by disrupting dwarf galaxies. Here's a very old simulation of stellar halo formation by Willock and Johnston, in which they had a constant potential into which they threw particle-represented live halos. They disrupted those, and the stars from those dwarf galaxies, color-coded by the origin, by the progenitor, formed the debris, the stellar halo, around the Milky Way, which is not shown in this animation. When you see the streams, there are two things that are important. First, streams reveal orbits to us. So in principle, if we can find a stream, we can rewind it back, and in rewinding it back, we can learn about the underlying gravitational potential. So there is a direct link to the orbit of the progenitor. Essentially, an orbit of the progenitor is drawn for us on the sky. However, streams are not orbits. There is a spread of energies and angular momentum to the stars that live in the progenitor. And this means when the stars leave the progenitor, the orbits will be slightly different from the progenitor and from each other. So let me just remind you how stellar streams form. So here's the familiar picture of contours of effective potentials in a two-body system, say Sun and the Earth, and there are Lagrange points. Of special interest are the Lagrange point 1 and 2 around the satellite. So stars, if I replace now the Sun and the Earth with the galaxy and its satellite, stars in the satellite can climb out of the satellite through Lagrange 1 and Lagrange 2. So the question, why would stars decide to climb out? And there are many different reasons that can compel them to go through Lagrange 1 or Lagrange 2. So as the galaxy, the dwarf galaxy, the satellite orbits the host, as it finds itself closer to the galactic center or to the disk, its tidal radius will shrink, so the stars will find themselves close to Lagrange 1 and Lagrange 2. If it was a globular cluster, the satellite was a globular cluster, the stars can be thrown out to the periphery, to Lagrange points, by two-body interactions. And of course, as the satellite goes through the disk and near a bulge, it is shock-heated, so the stars again are pumped to the periphery. So the stars that find themselves near L1 and L2 can leave the satellite. And some of them will choose to leave, and those that have left will form stellar streams. One stellar stream will be formed from stars that left the progenitor. So this is the satellite galaxy that orbits the host whose center somewhere under the floor. So the stars that left through Lagrange 2 will have high energies and high angular momentum compared to the progenitor. They will be on high orbits, so the orbital periods on high orbits are longer. So they will start to trail behind the progenitor. So similar picture is valid through stars that climb out through Lagrange 1. They are on lower orbits with lower energy and lower angular momentum. Those periods are faster, so they will start to leave the progenitor. So two tails will form, one in front and one behind the satellite. So here I'm going to illustrate this process by releasing swarms of particles at Lagrange 2 and Lagrange 1 every time the satellite goes through a pericenter. So here's the orbit of the satellite in some Milky Way potential, and I have marked positions of closest approach, the pericenter, and I'm going to release Gaussian clouds of particles that have otherwise the same systemic velocity as the progenitor. They have small Gaussian velocity dispersion in x and y. And let's see what happens. And I color code, red is leading and blue is trailing, and the different shades of red and blue are different sweeping epochs. You can see that with time, the stars redistribute themselves along the orbit of the progenitor, and the orbit of the progenitor is revealed. You can see that the ordering or the time of the release is still encoded in the stream. You can see the color shade gradation along the stream. So you can see individual stripping epochs still discernible in the stream structure. So that's interesting. And you see the individual streamlets start to separate close to upper centers for the trailing table. What I showed you earlier was the stellar halo in the Andromeda Galaxy. It's beautiful and it's a comprehensive census of streams which we can never hope to build in Milky Way, because we see inside the Milky Way we always have disk in the way, confusing the picture. However, in Andromeda you can never measure very accurate distances along the line of sight. It's also very difficult to follow the streams up with velocities. However, in the Milky Way, even though we don't see the entirety of the stellar halo, we can measure distances quite accurately. More importantly, we can obtain quite cheaply kinematics. We can obtain line-of-sight velocities by measuring spectra of stars. Now Gaia will measure proper motions, and the LSST will push the proper motion study even further. Moreover, we can measure the chemical abundances of the stars, so we can understand what the progenitors were. So progenitors represent this class of dwarf galaxies that were formed early on and destroyed, and we don't really get to study them anymore because they're not intact, but we can learn about the properties for the studies of the stream, which is an interesting subject in its own right. So when we want to study stellar streams, we need to use this kind of Swiss Army knife approach. We need to use different tracers, stellar tracers, because different stellar tracers are good for different things. For example, we want to use main sequence turn-off stars because they are abundant, because the velocity function of stars peaks and increases quite fast when you hit the main sequence. By the way, this particular plot is a density of stars with spectra in the plane of effective temperature and surface gravity. So this is basically a Hertzsprung-Russell diagram. And these are stars with spectra in slow neutral skyscraper database. And I've color-coded different interesting, useful stellar tracers that we can take advantage of when we study the stellar halo. So as I said, most abundant are main sequence and main sequence turn-off stars. We can use blue horizontal branch stars because they're good standard candles, similar to our Lyra, and they're very clean tracers. They're not contaminated by dwarfs or giants. And of course, we can use K giants and M giants because they're extremely luminous, so they allow us to reach into the outskirts of the galactic halo. Curiously, we can find the same sort of tracer. So this is how easy it is to pick them up with spectroscopy. Of course, spectroscopy only exists for a fraction of a percent in the SDSS database. Most of the stars have no spectroscopic fallout. But it turns out that for these classes of stellar tracers, you can also identify them pretty easily with photometry only. So this is now a color plane in which I color-coded regions offered according to what stellar tracers live in. So you can see that you can pick up main sequence turn-off stars and blue horizontal branch stars and M giants because they're all kind of outliers in this color phase distribution. So that comes in handy. So I've shown you how the Andromeda's stellar halo looks like. That's how the Milky Way stellar halo looks like if you use main sequence and main sequence turn-off stars. And here on x-axis is right ascension and y-axis is declination. And what's used here is again is the stellar density color-coded according to distance. So the redder stars are further away and the bluer stars are closer. And you can see similar picture. You can see that there are clouds of stars, there are streams that are broad. This particular stream is from Sagittarius dwarf galaxy, and you actually see two streams that appears to be bifurcated. There are thinner streams like this one, yet thinner and colder streams like the stream from the Palomar 5 globular cluster. So now you want to add dimensions to it. If you want to measure the gravitational potential, you need to extract as much information about the phase space of these substructures as possible. So now you need to switch the tracer. So we're going from main sequence Storinov stars into blue horizontal branch stars. So here's slightly different coordinate system, but it's still positions of stars on the sky. So I just rotated it that it's aligned with the Sagittarius stream. The panel below shows on x-axis is the angular distance along the stream, and on the y-axis is the distance along the line of sight. And you can see over dense arcs here and here, these are blue horizontal branch stars that are in the stream. And there are two tails that we see, leading that is closer and trailing that is further away. You can use K-giants and M-giants to trace the velocity track of the stream. So here I'm using the spectroscopic database and selecting a particular class of stars. And the selection box is shown on the right here. And if I go again in the along the stream direction and plot the velocity, line of sight velocity, there are very obvious tracks corresponding to the leading and the trailing tail. So you can see that this particular stream has two incomplete wraps, one leading and one trailing around the galaxy. So essentially, if you remember that animation that I showed you earlier, this corresponds to two loops, two petals of the Rosetta pattern that the progenitor draws in the orbital plane. And that's important if we want to now measure the properties of the galactic gravitational potential. So here is the measurement of the stream now with error bars. So essentially we model these density plots that I showed you earlier with a background plus stream detection. And we can extract the runoff distances, which is the top panel, and the runoff velocities along each of the tail of the stream. And you can see that the leading and the trailing reach upper centers, leading at around 50 and trailing at around 100. So the progenitor is at 0 or 360 in this plane. And every time the stream reaches the epicenter, the radial velocity has to go from 0. And the velocities are shown here. And you can see that corresponding to each epicenter, radial velocity indeed goes for 0 for leading and for trailing. So the radial velocity data makes sense and is extremely useful when we want to confirm or model these streams. If I go into the orbital plane of Sagittarius dwarf, here's how the detections that I just showed you look like. This is the galactic center, this is the sun, that's where we live. This is the location of the Sagittarius dwarf. And here's the leading tail, and here's the trailing tail. On the right, I'm showing the same detections in color, but the grayscale density underneath shows one of the most representative models of the Sagittarius dwarf disruption. So you can see there is something that is reproduced very well in the model of disruption and something that is amiss. What is not really matching very well, what's matching very well is the behavior of this leading arc and the beginning of the trailing arc. What's not matching very well is the further detections of the trailing. So you can see that in the model, in the disruption model, the trailing turns around and the upper center of the trailing stream is somewhere in the galactic disk. In the data, we see that it turns around much later. The epicenter is much further. So what does it mean in terms of dark matter distribution? So as I mentioned before, if we had an orbit, that should be the most straightforward way and most accurate way to infer, to measure the mass distribution. And that has been proven recently with the measurement of the supermassive black hole in the center of our own galaxy. Here is an orbit of one particular star that took slightly more than 10 years to almost complete. And this orbit looks like a Keplerian ellipse, and it gives you a mass measurement which has an error bar of order of 10%. And of course, this orbit has a size that is 10,000 times smaller than a parsec. Now we want to do the same experiment, but at distances that are 100 kiloparsecs. So many orders of magnitude, larger distances, encompassing a huge amount of mass, most of which is in dark matter in the galaxy. So this particular potential is really simple. It's dominated by the supermassive black hole. So it's a point mass potential. That's why the orbit is the ellipse, or in other words, the orbit closes onto itself. So if the mass distribution is still spherically symmetric, but is distributed along the radius, so it's not concentrated at one particular point in the galaxy, the orbit will not close. The orbit will start to precess, this ellipse will start to precess. And you saw this already in the little animation that I showed you. And the simple intuition can be, so imagine you have a center of the galaxy and a satellite that falls into it. And somewhere around the epicenter, it sees all the mass that is inside its orbit. As it reaches to pericenter, because the mass is readily distributed, suddenly what it realizes is that its velocity is too fast to the amount of mass that is inside the pericenter. So it overshoots. So that's why the orbit starts to precess. And of course, if you knew the size of the orbit and its eccentricity, which is essentially governed by energy and angular momentum of the orbit, the remaining factor that governs the opening angle between the petals, between the successive pericentric and apocentric passages, is the gravitational potential. Because we made the gravitational potential spherically symmetric, the only thing that is left interesting in it is the rate at which the density drops as a function of radius. So the slope of the density now controls the opening of the petals. So if you put all the mass in the center, so you make the slope extremely steep, the orbit will close onto itself. If you redistribute the mass as flat as you can, make a logarithmic halo, right? Then you open the petals by 120 degrees approximately. So if you can measure the apocentric precession, you can read off the density distribution of dark matter in the galaxy. And this particular polo illustrates exactly that. So here are different potentials. The potential here is a Power law, and this is the corresponding circular velocity curve, right? Rotation curve. So here's logarithmic with a flat rotation curve and a Keplerian drop and everything in between. So all that's changing here is the Power law index of the potential. And here's this Power law index from Keplerian to logarithmic. And here's the precession angle, so the opening angle between two successive petals of the orbit. And you can see, as you make the mass distribution flatter and flatter, the angle increases. So if streams were orbits, we could just use that plot, read the Power law index for the Milky Way, and be done. But streams, unfortunately, are not orbits. You can make a stream if you run an body code and you disrupt a progenitor and you produce a stream that looks like this on the left. So this is in the orbital plane, the distribution of debris from a progenitor which is now here. And this takes quite a long time because you're calculating the forces between all the particles in this problem, between all the particles that you put inside the progenitor. You can make it much faster if you avoid calculating the forces between the particles and if you give them particular initial conditions. And I already showed you what initial conditions you need to give particles if you want to produce stellar streams. You start them at Lagrange points. And that's exactly what we do here. So this is our model that mimics this N-body simulation. And of course it's much faster because we're not calculating the gravity between the particles, and we're given a very specific initial conditions, releasing these particles at Lagrange points. So in essence, we are solving constraint free body problems where the particles are orbiting Milky Way potential in the presence of perturber, which is the progenitor from which they are left. And it turns out that the gravity of the progenitor is extremely important. So here's the N-body simulation in the energy and angular momentum space. So these are the particles that left the progenitor and now form the trailing and the leading debris. So now if we just release the particles at Lagrange points without the gravity of the progenitor, that's what we get. These are the green distributions. So if we turn the gravity of the progenitor on, suddenly we get back more or less correct distribution of the phase space coordinates of our particles. So the progenitor is important, and I think I know why, but I don't want to waste my time explaining it now, but if you want to know it, I will try to explain it later. So now we have an extremely fast model that produces very good-looking, correctly looking streams, so we can now try to model the Sagittarius stream data that I showed you earlier. But before we do that, we test our model on mock data. And here the red curve is the true cumulative mass distribution as a function of radius in the mock data set. And our inferred mass is the black curve, and 1 and 2 sigma contours are shown in different shades of blue. When we apply the same method to Sagittarius stream, that's what we get. This is our inferred cumulative mass with 1 and 2 sigma contours. And here are previous measurements that mostly employ Jeans modeling. You can see that we go typically through the lower parts of these error bars, which is interesting, and also that our 1 sigma error bar is typically smaller than all previous measurements. So this work is described in a paper led by Simon Gibbons, who is a PhD student at Cambridge. So what we've managed to do is we've produced a new modeling tool that allows us to produce unbiased measurements of the mass distribution in the galaxy. We can hope to use this to also determine the shape of the dark matter potential. And we have ideas of how to use similar techniques to measure the dark matter Sahelo mass function. To understand the shape of the galactic dark matter halo, we now need to look at the precession of the orbital plane of the stream. So what I talked to you before was the precession of the apocenter, so-called apsidal precession. So the precession of the ellipse due to a distribution of matter along the radial direction in the host. So the orbit doesn't close onto itself and it rotates in the orbital plane. Now, if the dark matter distribution is aspherical, there will be torques acting on the orbital plane. So the plane itself will start to precess. So the orbit will precess inside the plane, and the plane itself will start to precess. So if we can measure the precession of the plane, we will determine how aspherical the dark matter distribution is. And this idea is not new. For example, Ibata et al. Already showed that if you make the dark matter halo very aspherical, streams like Sagittarius, so this is a spherical case, will start to spray around the galaxy due to differential precession of the stars in the stream. So they dialed down Q, which is the flattening, so they made it very flattened or blade, and very quickly the stream exploded. I'm not actually sure if this is feasible already or not. So a similar idea was explored by Valhauer et al., which also showed that to produce a stream like Sagittarius, you need a potential that is very close to spherical. But that's not what we're doing. We're not measuring the amount of spraying that is due to differential precession of stars in the stream. What we're more interested is the idea highlighted by Catherine Johnston, is actually measuring the plane of the debris and its evolution as you step through the stream. And so here is the coordinates of the pole of the orbital plane, basically where the angular momentum of the plane is shown on the sky. So these are L and B, galactic spherical coordinates. Here are the orbits, and this potential is flattened by different amounts, so here the flattening. And what they show is that, depending on the flattening, the orbital pole, the angular momentum vector, will draw these loops on the sky, and this path of this loop on the side depends on the flattening. So of course with the stream you're not measuring the orbit, but you measure not the orbital plane, but you measure the debris plane. So that they try to do this, they could measure the plane into the exact debris plane, in two positions along the stream. So that's what was known in 2005. And their measurements for the leading and trailing parts of the Sagittarius stream indicated that those orbital plane or debris plane are quite different from each other, of order 10 degrees or so. And they concluded that the flattening of the potential should be of order of 0.9, so it's an oblate, quite flattened potential. We have much better data now, so we can concentrate on the best studied part of the Sagittarius stream around here. So here I get rid of the background, the stellar halo background that is well mixed, and only have your density due to the streams. And there are two streams, one brighter and one slightly fainter. Because I have blue horizontal branch distances, I have now 3D information, and I can fit planes through the galactic center, because orbital planes have to go through the galactic center, and the chunk of the stream. And so I split it into red, yellow, green, and different shades of blue pieces, and for each I plot the orbital pole, or the plane pole on the sky. So this is again galactocentric LNB, and that's how the pole evolves as you step through the stream. For the bright, branch A, so this stream, and for the faint, so the upper stream, as you go, starting on the left and going to the right, the evolution is very different. So this is somewhat bizarre, because these two streams seem to indicate very different evolution in the same gravitational potential. So the sense of precession is different there. The precession happens in a different direction, and the amount of precession is different. What is important when we try to interpret this is to remember what Sagittarius dwarf could have been before it fell into the Milky Way. We think that Sagittarius dwarf was the third most massive dwarf galaxy around the Milky Way, after Large Magellanic Cloud and Small Magellanic Cloud. And we think so because we've calculated the amount of luminosity in the stream and put it back in the progenitor. So we have a limit on the total luminosity of the progenitor before infall by collecting all the stars and the streams. So this is the luminosity on x-axis and the mass on the y-axis using the dwarf galaxy models of Fokker and Rubian. So given the luminosity of order of 10 to the 8 solar, we get of order of 10 to the 9 to 10 to the 10 solar masses in the progenitor before infall. And given such high mass for the dwarf galaxy, it is likely that it was a rotating dwarf irregular. If the dwarf was rotating as it infell into the Milky Way galaxy, something interesting can happen. Every time the disky dwarf goes through the pericenter, it shows different part of its disk to the galactic center. And so the angular momentum in the disk will add to the angular momentum of debris different amounts of it will. So the sprays of debris that leave through Lagrange 1 and Lagrange 2 will have slightly different angular momentum and energy. So you can split streams into multiple streamlets depending on the orientation of the disky dwarf with respect to its orbital plane. And that's what Jorge Penarrubia shows here. These are different orientations, misalignment angles between the orbital plane and the disky progenitor. So 40, 0, 20, 20 in a different direction, and plus 40. You can see that when the two planes are aligned completely, this stream looks like the ordinary stream from a pressure-supported dwarf galaxy. But when you start to misalign them, you create these sprays of the debris that go off the orbital plane of the progenitor in different directions. And you create these bifurcations quite naturally. And so in the Penrubia 2010, the conclusion was that a progenitor that's misaligned by 20 degrees with respect to its orbit reproduces best at observations. But something interesting happens when you send a rotating progenitor in a spherical gravitational potential. So in a spherical gravitational potential, there are no torques acting on the stream particles, on the stream stars, so they shouldn't precess. However, in this experiment, we did exactly that. We sent the rotating dwarf into spherical potential, it disrupted, the stream is produced, and there are debris that are sprayed out of the progenitor after first pericentric passage, second and the third. And when we look at the evolution of their orbital planes, they're shown here. This is the pole of the plane, or angular momentum. They seem to evolve in very different ways and by different amounts, even though the potential is spherical, so there are no torques acting on these orbital planes, on the orbital planes of these stars. So that's somewhat surprising, but it's not very surprising if you remember that while there are no torques acting on the orbital planes of the streams, there are torques acting on the progenitor itself. And the progenitor itself is precessing, so the disk dwarf, the small dwarf galaxy that is rotating and is stripping as it rotates around the Milky Way as well, it's actually precessing under the torques from the Milky Way because it shows different parts of its disk to the Milky Way galaxy. So there will be, if it's misaligned with its orbital plane. So to understand this better, here is the orbital plane of the dwarf. Here is the orbital plane of stars in the dwarf itself. So this angle phi is the horizontal or in the orbital plane projection of the angular momentum of the disk. And the angle theta is the vertical component of the misalignment between the two angular momentum vectors. And you can see that a phi is evolving with time, and it goes through these very sharp evolutions every time the projector goes around pericenter. So it's precessing slowly, then very fast, and slowly again, and then very fast again. So because this happens, the debris configuration, every time the stripping happens, will be slightly different. So the stars will be sprayed with slightly different angles with respect to the orbital plane, with the original orbital plane. But what is also curious, what happens as well, is the vertical component of the misalignment, this angle theta, also goes through a dramatic evolution around the pericenter. So our original misalignment was 40, and it evolves by an order of 20 degrees along the orbit. So not only this disk is precessing as it orbits the Milky Way, it also wobbles every time it goes through the pericenter. And that's again because the orbit of the progenitor here is quite eccentric. So the arc around the pericenter that covers more than 180 degrees is covered very quickly. And so the disk of the dwarf sees the pull of the galaxy on one side and then on the other side in a short period of time. So it's torqued in one direction and then it rotates and torqued in the other direction. So it goes through this wobble. So if you want to model this, you could, because you know the gravitational potential, so you know the force, and you can write down the torque, and that's what we try to do. And that's the green line, and it's compared to the blue line, which is measurement from the body simulation. And you can see that you start very well, and then the two lines decouple. So your model breaks. And why it breaks is because because the moment of inertia tensor of the dwarf evolves away from the configuration in which you started. And it's a known effect, it's known as tidal stirring. So the disky dwarf is destroyed and it's slowly turning into a dwarf spheroidal galaxy. And if I have 5 or something, maybe an hour. How much energy do you guys have left? So this is a final topic, and I promise I'll make it very short. But I think it's very exciting because it's the question that everyone that is into this subject wants to have an answer to. How low is the mass of the smallest dark matter subhalo? And here's the idea that, again, has been around for some time. If you have a stellar stream and you have these small mass perturbations, these subhalos that are whizzing around the galaxy, they will start to hit the stream, right? They will puff it up. And so here's the paper by Ibatev in 2002. They produced a stellar stream by disrupting a globular cluster, and it looks pretty cold and collimated. And then they redone the simulation, but they also injected small subhalos with mass of order of 10 to the 6 solar masses that are now flying around and are hitting stream particles. And you can see what happens. The whole stream is broadened, is dispersed on the sky. So they hit the stream, and this effect should be observable. However, there is much more dramatic effect that can be seen and potentially used to measure even masses and properties of the dark matter subhalo. When the subhalo flies by the stream, it can tear a gap in the stream. So here are simulations by Yoon, Johnston, and Hall. So this is unperturbed streams, and on the right panel, these are streams perturbed by subhalos flying nearby. And here different velocities of subhalos are used. You can see that if you make the velocity really slow, the gap that opens is bigger. And here, for example, they dial up and down the mass of subhalos. And if you make the mass quite massive, so a few times 10 to the 7, the gap opens really wide. And if you have a low mass subhalo, the gap that's created is very narrow. In fact, there is a degeneracy between the velocity with which the subhalo flies by and the mass. And that's because all that happens in this flyby is that the subhalo imparts a velocity kick to the stars in the stream. And so this is the integral of the acceleration. So if you have smaller acceleration provided by a smaller mass subhalo, but you do it over a longer period of time, longer encounter, eventually you get the same velocity kick. So in this type of experiment, there is a degeneracy between the mass and the velocity of subhalo. But a very interesting pattern emerges. So these are profiles of these gaps. So these are star counts along the gap. And you can see there is a hole in the stream, but on either side there is a density enhancement. And this is a paper from Carlberg et al. 2013. So Dennis Urkel developed a very comprehensive, very clear picture of what actually happens. So here are different periods in evolution of the stream as the subhalo flies nearby. So this is unperturbed stream, and the subhalo flies nearby, nothing happens, and then very quickly there's a small period when all the stars that felt the velocity go towards the center of gravity, right? So they try to collect around the impact point. So there is a small period of compression. But if you give a star a velocity that is higher than its current velocity, just what will happen, it will go on a higher orbit, right? So in the coordinate system that is rotating with the impact point, this star will go on so it will receive the kick in this direction, it will go on a higher orbit, and will start to trail the impact point, because on the higher orbit the periods are longer, as I mentioned before. Similar thing happened for the star that received the kick in this direction. So this is the impact and the trajectory of the subhalo. So for the star that is also moving in this direction but received the kick in the opposite direction, it will go on the low orbit and will be leading the impact point. So even though stars try to congregate first near the impact point, they quickly reverse their motion and they go away from the impact point, and that's why the gap opens. Of course, the amount of the velocity, extra velocity, this velocity t amplitude, depends on how far the stars walk from the impact point. And so some stars receive higher velocity kick than the others, and they will start to overtake. So there will be a pile-up of stellar density on either side of the gap, and that's what is shown here. First the gap opens, and then there are higher densities, these caustics, on either side of the gap. I'll show you a quick animation of how it happens. So here's the stellar stream, this is the stellar density, and it's actually very long, very cold structure, but it's been spread out in y direction. So this is just 2 degrees across the stream, and 100 degrees if you pay attention to the axis layers in the longest stream direction. The stream moves that way, and the subhalo flies by, perpendicular. This is in the coordinate system that moves along with the stream. That's why you see this cyclic wobbling up and down. And you can see how this region is evacuated and the stars start to pile up on either end. This signature is very unique and very particular, and this imprint of the interaction is very particular in every phase space coordinate of the stream. And it depends solely on the velocity key. And here is the velocity key as a function of distance from the impact point, where it should be 0 by symmetry. And it should be 0 at infinity, so it goes for some maximum. So there is a characteristic scale at which the velocity kick is maximum. So all the information about the subhalo flyby is in this curve, in the curve that represents the velocity kick as a function of distance from the impact point. We have actually done an experiment in which we generated streams, created signatures due to subhalo flybys, and then produced mock data. Basically, we observed this stream with Sloan, LSST, DS, Gaia, and tried to measure the properties of the subhalo. And what we show is that if the perturber, completely dark, it has the mass of 40 of 10 to the 7 or slightly higher, you can infer all its properties, including mass, and all 3 components of the velocity, the scale radius, and the impact parameter, and even the time of flyby. So I think the time is right now to go and follow up the streams that we know exist, like the GD1 stream, and try to find these signatures, because we now know how to infer properties of dark matter subhalos. I have conclusions, but I think I more or less gave you the conclusions as I went along. So the important thing, we have fast stream models, we know how to generate streams. The stream production can be extremely complicated if the dwarf progenitor was not a simple pressure supported system, but there are interesting information that is encoded in the precession of these streams too, so we can extract it, I hope, and learn about the shape of the dark matter halo. And probably most exciting is that we now have a very clear insight into how the gaps form in streams. That gaps are not just holes in streams, they have very particular signatures in all 6 projections of phase space. So if we have an undeniable signature from the flyby, we know now how to measure the properties of the dark matter subhalo that created it. And I stop here. Thank you.
So, questions, and traditionally, first students and postdocs.
No. Do you pay them money to ask questions?
Oh, you pay money, but not so much.
That's why they're not asking. So as I said, all the information is in the shape of the velocity kick as a function of distance along the stream. So this shape will be slightly different, and as a result, this shape will be slightly different. So this is the density profile of the gap will be slightly different. So you will have to model it if you want to extract this information. But that's probably going to be quite difficult. So a spherically symmetric assumption is probably fine for the moment. But yes, if you have very accurate measurements, and basically what you need is lots of stars to measure the density evolution as well. You could probably tease out properties of subhalos like asphericity or whether they have cores or cusps and so on and so forth. So it's all encoded in the structure that the flyby creates. It's like you use stars for tomography of the subhalo. Essentially, stars feel the pull from the subhalo, and if it's extended, and then they will feel slightly different pull. And if it's extended in an interesting way, the stars will feel the pull in a particular way, which will be encoded in the shape of the gap. So I think it's in dreamland, but yes, you could maybe tease out this.
So have you calculated what is the probability to have such an encounter?
Yes, I haven't, but someone else did. I think it says there, Yoon, Johnston, and Hall calculated that there'll be 5 encounters for typical PAL 5-like stream over its lifetime with subhalos of order of 10 to the 7.
Given the streams that we have,
Yes.
in the nuclei,
This is the stream.
it already plays upper and higher limits to
I personally think that if you look at this picture, which is the best cold stream, the longest cold stream we have, you can already see lots of gaps here. But I personally think that those gaps are to do with data quality issues rather than with subhalo flybys. So what we're trying to do now is to go to telescopes with wide field cameras and say, let's follow this up and let's see whether these gaps are real or are caused by bad seeing or clouds on the night when the observations were taken. Something to do with star galaxy separation and with subhalo flybys. So I think we're now in a position to see if this exists or not. But I think it's slightly early. Ask me again next year.
Further questions by students? Okay, then let's open. I'm going to do an experiment. I'm going to get the microphone to the people. Maybe that's actually useful. The question askers can use better the microphone than me, and I don't know what to do with it.
Oh, thanks.
So it's following the last question. So you said you had about 5 events for PAL 5 during its lifetime.
Yeah.
And you are interested in the subhalo mass function in the Earth.
Yeah.
So what are the other candidates and how much events do you need in order to estimate with more or less accuracy the mass function between 10 to the 7 and 10 to the 9?
I don't know an answer to this question because I think we haven't carried out this experiment. So we are at the stage where we want to find the signatures and try to infer masses. I think this question is right, it's a good question, how many streams you need to follow up to constrain the mass function. However, before we do that, we actually want to move from this idealistic setup when we had a simple potential, a clean stream which we perturbed from subhalo flyby, with a situation much closer to reality, where we have a cosmological setup, the galaxy grows, subhalos fly by, streams are perturbed. What actually it will look like in that case will be probably much more complicated than that. So I think we want to address that question, how to extract information from realistically perturbed streams before we go and try to build mass function. Because those streams probably have felt the evolution of the potential. So it's kind of, I think, too early. But I think it's a good question, but I don't know yet the answer. The interesting thing here is that once you put constraints on the flyby, not only you know the mass and the scale radius of the perturbator, but you know roughly its trajectory, so the velocity and the impact parameter. So you can probably start to rule out whether it was a dwarf galaxy that is known to orbit the Milky Way that would have caused it, right? Because the biggest signatures will be from most massive perturbers, obviously. So.
I mean, Vasily, when you said initially that you can calculate the streams backwards, that makes the assumption that the potential of the Milky Way did not change dramatically
Yes.
over the past several gigayears.
Yes.
How good is this assumption?
I think this is a, I love when the speaker says this is a very interesting question. It's a very good question. Normally means that they don't know how to answer it. Or they're going to say some bullshit, but like I'm going to do now. Well, I think it depends on the mass accretion history, right? So, in the Milky Way, I have very strong belief that the mass accretion history has been quiescent in the last few years. We have many lines of evidence that all agree that Milky Way hasn't accreted much until Magellanic Clouds fell in now recently. So there was a period of calm. In that respect, I think the last 6 or maybe even 8 years in the Milky Way were quiet. So this assumption in the Milky Way probably holds, and I can explain why I can make this assumption. But in Andromeda, that's not a good assumption. And that's why we actually want to do this experiment of trying to model streams in cosmologically motivated setups, where this be the potential holds.
It need not necessarily be the accretion of new material. It could be tidal torques exerted by the Andromeda galaxy, for instance, right?
So the Andromeda galaxy is probably too far away and has been quite far away for a long time to exert torques, but what I think has been shown to matter a lot, and it's only kind of came into the light recently, is the Magellanic Cloud infall. So the Magellanic Clouds have always been assumed to have mass of order of 10 to the 10 solar masses, which is interesting but not that scary. But recently, there's many observational facts that point towards Magellanic Clouds being, or LMC in particular, being quite more massive than that, so 10 to the 11 or so. So this is now slightly complicates the picture because the Milky Way will rebound as a reaction to the pull from the Magellanic Cloud itself. So everything will be perturbed. The experiments we have carried out to see how much effect this will, how much perturbation this will cause on the streams. So far what we've seen is that it doesn't really change the picture dramatically. So the effect is quite small and we can think. But I think that's the only perturber that I can think of, in the last, few years. Otherwise, Milky Way is actually a nice and quiet place, it seems. A boring place, if you want.
So, coming back to the modeling, I mean, you describe this as a transformation between the different types of galaxies, but it will also, the modeling will also cause an increase in dispersion. So, for example, in branch A and branch B, or whatever you call them, two branches, would this be detectable? I mean, I expect that the dispersion changes. Would this be strong support confirmation of that this actually happened? In addition to all the photographic and all the structural changes.
Next question.
Yeah, but I think it all depends on. You're probably right. The dispersion will change, but the question is by how much, because the velocity dispersion of the stream changes along the stream because there is basically the stream stretches and compresses as you go through it, depending on the orbital phase of the debris. So there is no such thing as a velocity dispersion of the stream, right? So that already can be a change by a factor of 2 to 4. right? So I don't think the velocity dispersion changed due to, essentially, you see in the rotational component of the progenitor through different lines of sight, which is what is causing this different. I don't think these will be much bigger than that. So it will be the same order of magnitude or less. So it will be very difficult to tease out because you're looking at something that's constantly evolving. So I think it's an interesting suggestion, but I think it needs to be tested how this effect, what's the scale of this effect compared to the secular change of the velocity dispersion. But I think it's an interesting point.
So let me try to phrase this in a way that's answerable. Part 2 of the talk, you said that the wobbles of the disk.
Yes, it's precessive and wobbling. It's
Yes.
doing two. Yes.
The random motion, dynamical motions of the disk spread the stream out. In part 3, you say that you can put a lower limit on how, or an upper limit on how, a lower limit on how good a mass you can detect. But you didn't combine those two.
The important thing is that two different streams. Sorry, I'll let you finish the question.
Well, maybe you've just answered it, but isn't the wobbling going to make it harder to detect the low mass objects?
So the potential, the mass and the shape of the halo overall, my suggestion is that we try to use Sagittarius stream for that, because it's the longest, most luminous stream that reaches out to 100 kiloparsec. So it's the right thing to use. The Sabatier mass function, you need to see the difference. So these velocity peaks are really small, right? So you need as cold a stream as possible. So I suggest we use globular cluster streams like this one here to do one thing and a big dwarf galaxy to do the other. And so globular clusters probably do not rotate like much. So I think this worry in particular is alleviated. So.
Is there further questions? We had already a number. If not, then let's thank Vasily again.
Thank you.